Hello, my name is Thomas de Boer, and today I will be presenting my poster titled Richter Predictor, Identifying Precursors to Induced Seismicity in Casing Deformation. To provide some background, this poster presents the application of, and case studies associated with, the field implementation of a novel technique to predict and mitigate seismic risks. The underlying technique analyzes changes in wellhead treatment pressure during completions, identifying aseismic slip events that may be missed by traditional monitoring methods. Previous work conducted in this area of study focused on the identification of anomalous, high-energy resonant behaviors within surface pressure data present in historic data. Further development of this core idea shows that the original concept holds true across multiple stress regimes, different failure mechanisms, and during active hydraulic fracturing operations. The approach discussed herein enhances our understanding of induced seismicity mechanisms, as well as proposing practical solutions for improved seismic monitoring during hydraulic fracturing. The poster discusses a conceptual model for aseismic slip processes and highlights a technological solution to mitigate risks. Insights from several case studies are presented, highlighting the efficacy of the algorithm across different deployments. In addition, the future implementation of the technique on high sample rate data across multiple data sources is discussed. This presents a roadmap for better separation of sources and an improvement over the amplitude-based approach, which is what is discussed within this poster. The purpose of this is that during typical hydraulic fracturing, high pressure fluid is injected into a rock formation to induce fractures and increase the permeability of the rock. However, as the industry moves towards more infill wells due to the decreased virgin acreage, challenges associated with fracture behavior affects completions and increases the risk of adverse events. When we say adverse events, we mean along a sliding scale. At the small scale, those events may represent things like less complex fractures, which can extend between wells, causing parent-child or child-child fracture-driven interactions, or FDIs. You can see in the top diagram here a representation of typical fracture behavior in which a fractured zone develops around a wellbore and is relatively well contained in the near wellbore. However, in areas where we have more dense wells, what we can see is that there's actually interactions between these wells, and these interactions may have a negative impact on production. Beyond that, if we look at the in situ stress state in the presence of pre-existing structures such as fractures, bedding planes, or faults, stimulation near these structures may induce both large-scale deformation, which occurs as a seismic slip, which increases the risk of adverse events such as induced seismicity or casing deformation. Essentially, in the near wellbore, as those planes coalesce or those pre-existing structures begin to activate, as they're pressurized by the fluid or as stress changes near them, they may be prone to this large-scale deformation. When the wellbore passes through one of these planes, for example, if the vertical section of a wellbore passes through a specific bedding plane, or if the lateral section of a wellbore intersects with some pre-existing fractures or faults, as deformation occurs on that surface, it may induce deformation in the casing as well. Beyond that aseismic slip has the potential to interact with larger scale structures, such as critically stressed faults, and that deformation process may alter the stress state on those pre-existing faults, inducing seismicity on those faults or triggering large-scale fault rupture. And this aseismic slip has implications beyond the regulatory impact of induced seismicity, as it increases the risk of back casing deformation, which can result in understimulation, incomplete stages, or complete lost acreage if the damage to infrastructure is too severe. The methodology, as I mentioned previously, is primarily based on the analysis of the surface pressure signal or the discrete oscillatory behavior contained within the surface pressure signal recorded at the wellhead. On the top side here, You can imagine if we have a plane that is shearing within the subsurface, that plane can generate an oscillatory motion, which would be repeated at regular intervals, which may be transmitted through the rock as a seismic wave and collected either with a downhole or a surface geophone. You can see here the spectrogram for such a surface geophone, and you can see within this spectrogram several bright lines. These bright lines represent, at a specific frequency, a large amount of energy is being released. In contrast to a geophone, if we look here at the bottom side, you can see if we have a wellbore, which is connected either directly to a deforming plane, or those seismic waves are able to transmit and interact with fluid-filled fractures. Those seismic waves may then be propagated through the fluid as pressure waves, and those pressure waves may transmit up the wellbore towards the surface, where it can be measured by our surface pressure gauge at the wellhead. On the right-hand side at the bottom here, you can see a similar spectrogram as above, this case looking at the signal captured by a surface treatment pressure gauge. You can see within this treatment pressure gauge, we have very similar resonances, and in fact, similar frequencies of resonances to those captured by the geophone. This case shows the spectrograms that were collected at the same site at the same time for the same duration. And we can see that the signal between these two sources is analogous. And essentially what this allows us to do is treat our surface pressure gauge like a distributed hydraulic antenna. This allows us to capture seismic waves that are transmitted through that fluid pressure collected at the wellhead, and these can be transmitted and processed in real time using an advanced signal analysis and decomposition technique. This signal analysis technique produces a second-by-second measure of the resonant energy contained within the various frequency ranges of the pressure signal. The total energy released within each completion stage is summated and normalized to the duration of the stage to produce a metric called derivative energy, which enables us to monitor that deformation risk by assessing when and where these resonance signals are occurring. As this surface pressure can be streamed in real time, this allows mitigation strategies to be implemented to limit the progression of aseismic slip as it is detected within the pressure, reducing the risk of casing deformation and induced seismicity. The first case study covers the occurrence of bedding plane slip within the Montney Formation in British Columbia. Presented here are three different pads over which we have measured the resonant signal present within the pressure and decomposed it and produced the derivative energy metric. Those derivative energies are plotted across a 2 to 3 weeks completion, where each dot here represents one single stage of completion. You can see here on the vertical axis, towards the end of this pad, we see a sharp uptick in energy. That uptick in energy directly correlates with when we were able to detect, using caliper logs, a deformation process that took place over approximately 4 to 6 hours, in which the verticals of these wells saw increasing deformation over that period. On the second pad, we can see a similar trend where there's some early release of energy, and toward the heels of the wells, we see again a sharp uptick in energy. In this case, mitigation strategies were in place by the operator in order to attempt to reduce the severity of this aseismic slip process, and those mitigation strategies were ultimately more effective than in the previous pad. In this case, there was moderate casing deformation detected using caliper logs. However, completions were able to finish with slightly reduced stage volumes. In the third case, we can see again a similar thing where we have an initial release of energy. We progress along towards the heel of the well. We start to see an uptick in energy. However, at this point in time, more severe or more forward-thinking mitigation strategies were in place, and those were evaluated using this technique, and it effectively showed that those strategies worked. There was relatively minor casing deformation detected on this site, and overall, there was a much less release of energy detected using this method. The second case study presents a two-well pad located in a strike-slip fault regime. with multiple pre-existing offset fault structures. These pre-existing structures were noted in 3D seismic surveys that were completed prior to the completion of these two wells. On the left-hand side, you can see an approximation of the plan view, with well A shown in red and well B shown in blue, which corresponds to the different energies shown on the right-hand side. In addition to that, you can see 3 offset structures, structure 2 in green, structure 3 in purple, and structure 4 in orange. During completions, several induced seismic events were recorded on these fault structures, which are shown here in figure 11b. The largest event detected during completions was a 3.01 local magnitude on the 4th structure, located within 500 meters from well B. What we see is that during the activation of these various fault structures, we see a consistent increase in energy in these two wells. And just before the magnitude 3 event, we see the highest energy in a stage in well A. That very high energy release occurred approximately 1.5 hours prior to the magnitude 3 event, and a warning was sent to the operator that anomalous behavior had been detected, and this was indicative of a high risk of a larger induced seismic event occurring. The third case study depicts a similar setup to the previous, with a 2-well pad that is located in a strike-slip fault regime. The difference here is that this case study presents a pad that was located near previously activated structures from other offset wells. The largest event detected during completions was a magnitude 3.2 local, and it was located within 2 kilometers from the pad. In this case, the largest event occurred further offset from the pad than in the previous case study, on a fault structure that had been previously activated. Additional large events did occur during this peak of event counts just after the highest peak in our derivative energy, as you can see here. The peak in derivative energy was noted approximately 24 hours prior to the 3.2 magnitude event, and that high energy was sustained throughout the activation of a nearby fault structure to the wellbore. It's believed that the deformation on the near wellbore structure induced a stress change on the further offset fault, which triggered it to fail with a larger rupture at a 3.2 magnitude event. The near wellbore fault structure had several events, some of which were in the range of 2.5 to 3 magnitude. Previous case studies above show the result of an algorithm that was designed for filtering and extracting various resonant components identified in the 1 Hz sample rate surface pressure measurements. These are relatively standard measurements that are taken across almost all completions. However, due to the nature of the low sample rate, it's not possible to retain true information on the source frequencies which are captured in the data, and this presents a barrier towards developing a detailed understanding of the underlying mechanisms of fault rupture. In contrast, generally, geophone waveforms are collected at a much higher sample frequency. For example, on the right-hand side is a spectrogram of a geophone that was collected at 250 Hz, showing the spectrogram from 0 to 125 Hz. Within this spectrogram, which is precursory to a 4.6 magnitude event that occurs as this bright vertical line here at approximately 2015, we can see the occurrence of several resonant behaviors in the 0 to 10 Hz range, which are believed to be tremors that were active. Beneath this is a spectrogram of a higher frequency surface pressure that was sampled at 50 Hz, and we can see the range from 0 to 25 Hz shown here. In this example, we can see similar behaviors that occur with tremors occurring in the 0 to 15 Hz range. Some of these tremors may be induced, or some of these resonant behaviors may be induced by the pumping behavior at the surface. However, at approximately 4 MST, we get a 3.2 magnitude event, the one referenced in the previous case study. In this case, we can see lower frequency harmonics that extend throughout the stage just prior to that event. Based on that, further study on higher sample rate pressure measurements when compared to geophone waveforms captured in a similar environment reveal the presence of distinct tremor-like signatures that are evident in the lower frequency range. By using high sample rate pressure measurements, it's possible to fully separate the lower frequency tremor-like behavior from the higher frequency resonances that are typical during stimulation, enhancing the ability to detect precursors to large seismic events. Future study will focus primarily on the capture of this high frequency pressure data. The deeper analysis of this using similar techniques as to what was presented within this poster, and the application of identifying specific frequency ranges for specific sources as we understand more what deformation processes lead to induced seismicity and casing deformation. With that, I'd like to thank you for listening. Please don't hesitate to reach out if you have any further questions. Thanks.